Hey guys, your boy Chili here. Welcome back to Multithreading with C++, C++ multithreading. I don't know, whatever you want to call it. Last video, we established our problem, our issue that requires a tissue. And to put it two words, it is, let me see here. So when we process a number of elements piecewise, that turns out to be significantly slower than if we had processed the same number of elements but all in one go. This is the piecewise implementation. We split it up into 10,000 smaller work pieces and iterate through those. And this is the full, just all in one go. And this one's slower. It's 2.5 times slower. And I asked you guys why? Why is it slower? And I will tell you why, the big reveal. But before that, I just gotta talk about a little bit of a slip up that I made. So my intention here was to have this grand total and to, add all of the subtotals together every iteration and accumulate that into the grand total, but I'm not accumulating here. Funny thing is, if you run this, you actually get the correct answer. So it'll take a little bit. Yeah, 1, 2, 2, 2. Remember those 4 digits. And now we'll run it in the other version and it will say 1, 2, 2, 2. Yeah. So it works for the wrong reasons. My intention was to accumulate in here. The reason why it works is because, well, it's kind of like modular arithmetic kind of deal with the overflows. The reason why it works is, because we're just adding into each one of these individually. And we're not erasing them every iteration. So they're just accumulating separately. And then they're being added together at the end. They're being added every iteration, but only the last one counts and only the last one is necessary. So I didn't even really need this grand total. So let's get rid of it. I don't know. Who cares? I'm just going to put this here. And so that's more like what we had before. And we've simplified our code by a wee bit. And that's fine. All right, now let's get into the meat of the topic. So, why are you slow? And I hinted at it in the last video. It's not the loop. It's not an additional loop. That doesn't count for crap. Nobody cares about that. It is the fact that we are spawning lots of threads, right? We are spawning 10,000 times 4 threads, right? And then destroying them. And that is expensive. It is an expensive operation to create a thread. In C++, we're pretty used to being cheap to create most of the things that you can create from the standard library, like a vector or whatever. Even allocating a large vector is, it's relatively cheap, I guess. I don't know. There are things about that, you've got to allocate additional virtual pages into your heap if your heap has to grow. But overall, creating a thread is much more expensive. It calls into the operating system. The operating system has to create the context for that thread. And that includes, allocating the memory for that thread stack. Every thread has its own stack, and that's like a megabyte or whatever you set it to. So it's expensive. It's a heavyweight operation to create a thread. And so if you're creating a lot of them, that is going to start to become expensive. In fact, the creation of the threads in this case, if we're breaking it up into 10,000 work pieces, is 1.5 times more expensive than the actual processing itself. So, you might say, well, then you can't break things up small. But like I said in the previous video, breaking things up small is sometimes something that you have no choice in. Sometimes the data is only coming in a little at a time. You don't have the ability to process it all at once. You can only do it in small chunks. And, other times you don't want to have a big, long process that blocks for 1 second or 10 seconds. You want to do it in small pieces and then update those results incrementally. Like, for example, a game. So, we want to do this, but it is very slow. What can we do? Well, the answer is don't create so many threads. But then how do we do the work, dispatch the different jobs, and then wait for those, jobs to be done so that we can use the results? And the answer to that question is, well, instead of passing in the information in the creation of the thread and then joining and waiting for the threads to die, basically, to finish, we keep our threads alive. We call them our worker threads. We keep them alive, and then our master thread is going to periodically communicate with the worker threads and dispatch jobs to them. It's going to say, okay, here's a new job, go do that job. And then the worker will do the job, and when the worker is finished, the worker will somehow signal back to the master, okay, I'm done, you can use the results. And then the worker will sleep. And, you know, the master thread will use the results, and then they'll have another job, and they'll say, here's a job, and then it'll give the job to the worker, and then the worker will work on it, and then he will signal back. So we keep these workers alive, and then we only have to create them once. What's the drawback? There's no free lunch chili. What's the catch? Well, the catch is now you've got to do all this synchronization from the master to the worker and from the worker back to the master, saying, you know, I got some work for you. That work is done. And that is more complicated than just, you know, spawning a thread with the data set in the parameters to the function, to the thread constructor, whatever, and then joining on that thread, waiting for it to die. That's very simple. This is more complicated, but it's going to be faster, and thus it will be worth it. If you have to, you know, you have to do a large data set piecemeal. If you don't have to do it piecemeal, then just do the join method, fork and join, or whatever you want to call it. Don't do this bullshit that I'm going to show you in this video because it's way more complicated. But if you do, if I did it, here's how. Okay, so now we have to discuss, okay, well, what's the mechanism that we're going to use for this synchronization between our threads? And I mean, one way you could do it with just the stuff that I've already taught you is you could have flags. I'll just call it like a flag, some shared data with, so this is the job data, and then a flag. And what the master would do is he'll, first of all, will protect all this with a mutex. So the master will get the mutex, will, you know, write the data for the job, and then he will set the flag. And the worker will have to poll. So the worker will have to sleep, you know, for, I don't know, like 10 milliseconds. And every 10 milliseconds, it'll wake up, it'll grab the mutex. And if the master is still writing here, it'll have to block and wait for the master to stop writing. When it gets the mutex, then it will check the flag, and it will say, oh, I've got a job now. And then it will start executing the job. And when it's done, there will be like another flag. Maybe this is the done flag. And it will, you know, it'll erase this because it's done, and it'll do the done flag. And the master will also have to be sleeping and will poll the done flag. And when it's done, then it'll say, okay, I got work. And then it will take the results. So this is the polling solution, and it's wasteful. It's wasteful in a couple of ways. First of all, it's wasteful in that these threads have to be, you know, constantly waking up, constantly grabbing mutexes and checking, and that's wasteful. But it's also wasteful because let's say there's the master is polling every 10 seconds. So we sleep, here we check, we sleep for 10 milliseconds, then we check. If the worker, we check here, worker's not done, we go to sleep, the worker's done here, we could start, you know, using those results here, but because we have a polling period of 10 milliseconds, this time is just wasted for no reason with your thumb up your butt. So polling sucks. Polling is not sexy. It's very easy to conceptualize. It's not sexy. What I'm going to show you is sexy, but it's harder. So in C++, we have the thread support library. It has thread, it has jthread, it has I don't know. Is it like the mutex? Yeah, lock. Some things we've shown you. And it has something here called condition variables. And this is the thing. It is a powerful primitive that allows one thread to basically signal another thread. A mutex is for preventing two threads from accessing the same data at the same time. But it makes for a pretty crappy signaling mechanism. That's what condition variable is for. Now, I don't like the name condition variable. I just like to think of it as like a signal, but whatever. That name was probably taken in the original P threads or whatever for another thing. Who cares? So, what is a condition variable? Well, you got a condition variable, and what it allows you to do is you can have threads that wait on the condition variable. So this thread, let's color code it. So this worker is going to wait on this condition variable. And you could have multiple threads waiting on the same condition variable. And then a different thread can call a notify function, and that will cause, depending on which notify function you call, that will cause one of the waiting threads to wake up or all of the waiting threads to wake up. So I can call one function, send a simple signal, and everyone wakes up at that instant. And that's beautiful. Then we don't need polling. Very simple, right? Well, not really. So a condition variable needs a condition. The way it works, the theory of it, and how it's typically used, how it should be used, is you've got some kind of shared memory, some kind of shared variable. It could be something simple as like a Boolean flag. Flag saying it's time to do something. And, instead of your worker polling that flag, you are going to set it and then notify the condition variable. And then the worker will not require polling of the flag. Now, because this is shared memory and everything, you technically, and again, I'm going to probably say this a lot, but a lot of this stuff, it applies to the abstract machine that C++ targets, and it can be different on different platforms. So some of this stuff that you are required to do, you can actually get away with not doing on x86, but you should probably do it anyways. But anyways, I won't get into that too much, I guess. I'll try to do the best practices thing. But so with a condition variable, you've got some shared memory. You should protect it with a mutex. And in fact, condition variable must be used together with a mutex. That is a 100% solid requirement. You cannot use it without a mutex. So the way it works is you would grab the mutex, you would alter the shared memory. You then release the mutex, then you notify the condition variable, and if this guy's sleeping on this, he will wake up. And when he wakes up, the mutex is automatically acquired by the worker that wakes up. And then you check the condition. You always have to check the condition. Even though, like in this condition, the only reason you would call notify, and so theoretically the only reason you would wake up is because this was set. Even if that's the case, you still have to check the condition, and I'll get into that a little later. It's a weird thing. But you check the condition, and then you probably do some work. Now, like I said, when the waiting thread wakes up, it atomically, at the same instance of waking up, has the mutex. And the way this works is that you actually, when you go to sleep, you have to give the condition variable a mutex or a lock. So you acquire, when it's time for this worker to sleep, the process is weird, but it took me a little while to wrap my head around it the first time as well. But there's a process, there's a sequence to it. When you want to go to sleep, you acquire the mutex with a lock, and then you call wait and you pass it that lock. And when you call wait and pass it the lock, the wait function of condition variable will unlock the mutex for you. And then the next time you wake up, because of notification, it will automatically acquire the mutex again. So what that means is that the mutex is guaranteed to be held while you're awake. Unless you manually release it at some time during your waking hours, when you're going to sleep, you have the mutex. When you sleep, you release the mutex. And the second you wake up, you have the mutex again. And that becomes important. That prevents race cases and stuff like that. And even if you think you don't need it, it doesn't matter because the specification says you have to do it. The thread that intends to modify, the thread that intends to wait has to acquire a mutex and so it checks the condition. You should check before you go to sleep. Because if you're going to sleep, but the thing that you're waiting for already happened, you'll be sleeping forever because it already happened. So you have to make sure it hasn't happened already before you go to sleep. And then you execute wait, and those will automatically release the mutex. And when the condition variable is notified, the thread is awakened, the mutex is atomically reacquired, and then the thread should check the condition. And then there's a way of basically wrapping all those 3 steps up into one clean package, and that's what we'll use, but the idea is the same. And for the one that notifies, like I said, you acquire the mutex, you modify some shared memory while the lock is held, and then you execute notify, and you can release the lock before you do that. And you should release the lock before you notify. Otherwise, the thread that's getting notification will wake up and it'll immediately block on the mutex until you release it. So that's just wasting everybody's time. But anyways, so this has been a lot of talking, but that's because condition variable is kind of complicated. It's a complicated boy. So now we're going to do it, but the video is already like pretty long, so I'm probably going to cut it here. I could just in this video quickly, explain how we're going to organize this stuff. And then that means the next video, we can just get right down to the coding. So that's what we're going to do. So basically, the way it's going to work, I'm going to wrap the workers now up into like an actual object. So there's going to be a worker object. And there's going to be a master control object. And those are going to encapsulate a bunch of variables that we need. So every worker, this is the worker. Let's say that the small block with the W is the worker thread. And that's encapsulated now in the worker object. So every worker is going to have a pointer back to, well, not the master thread, because the master thread is just the main thread. But there's going to be, so an MCTRL, master control. And every worker is going to have a pointer back to the master control. And this is what it's going to use to notify the master control, I'm done. It's also going to have, so we're going to have the thread, which is a J thread. What the hell? What is that? J thread. Well, that's more like it, but still pretty bad. It's going to have the condition variable. I'm not going to write it in both of these, so you can just assume that it's the same in both of these. Condition variable, mutex. You got to have mutex with condition variable. It's like a horse and carriage, love and marriage. We're going to have our span. So this is the shared memory that's protected by the mutex. We're going to have the span. We're going to have pointer to the output, which is pointer to int. And we're going to have a flag, a Boolean flag, that says whether this thread is dying, because we need a way of terminating the thread. The thread will, after it's done any given job, it will go back to sleep and wait for a new job. So we need a way of telling the thread, okay, there's no more work. You got to die now. Time to die. Like tears in rain. Anyways, so this is the stuff that we will encapsulate in the worker. And then there will be some simple member functions that we call from the control to set the job and to kill. So set, not sat, set and kill. Man, this is really bad. My diagrams are getting worse and worse. Anyways, so yeah, that's the worker. And then the master control. This is going to hold the condition variable that will be used to signal the master thread, and mutex, because you always have a mutex with a condition variable. And I think we'll put a lock in here. For these ones, the lock will be in the thread's main loop. It'll be a local variable, but here the lock will be part of this structure. And what else? Okay, so here's the thing. Here's the stuff that'll be protected on this side. Well, there's really only one thing that'll be protected. So we're gonna keep track of the total number of workers. So worker count, and then we'll have in the protected memory, protected by the mutex, the done count. So what'll happen is when a worker thread is finished, it will grab this mutex, increment the done count, check if the done count is the same as the total number of workers. Because if the done count is the same as the total number of workers, that means that all the workers are done and it's time for the master to wake up and process the results. So if these are the same, then the worker thread that did the last incrementing will also notify the condition variable and say, hey, it's time for you to wake up. The work is all done. And this will also be, encapsulated with some very simple and easy to understand interface functions. So this one will be, I don't know, like notify done or something like that. So yeah, this is the way we're going to live our life, and it's going to be very cool. Fortnite and Cola, yippee. But yeah, so the coding will come in the next video, and it's gonna be a wild ride. Until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button, helps a lot, and I will see you soon with some more C++ multithreading.